Wanted to welcome everyone to the October Liftoff webinar featuring Altair and the topic of lightweight metals enabling software. My name is Joe Steele, calling in from the Lift headquarters here in Detroit. Want to thank everyone for joining today. A couple of housekeeping items before we get started. I wanted to have everyone put their phone on mute. I try to put everyone on mute myself, but in case someone slipped through the cracks, wanted to make sure that there's no background noise from any of your busy office locations. If you have any questions, please go ahead and use the chat function that is on the GoToMeeting taskbar it's on my right side of the screen. You can send your questions to the organizer, and I will help facilitate those at the end of the presentation. And also wanted to remind you that each Liftoff webinar is going to be recorded. So we're recording this session, and we will post it on the Lift website for future viewing. If you'd like to watch it again later, if you'd like to share with folks who were unable to join, I would encourage you to do so. It is on the pull-down menu on the lift.technology webpage, the pull-down menu under technology called the Liftoff webinars. So you can go ahead and take a look at this one, or take a look at the sessions we've had in the past, and you can also take a look at the speakers we have planned for the future. Wanted to give you a quick update on Lift. For those of you who might not be familiar with what Lift is, we are Lightweight Innovations for Tomorrow. We are one of 14 federally funded manufacturing innovation institutes called Manufacturing USA. There are 14 of us around the country. We are based here in Detroit, and our focus is on lightweight metals. Each of the 14 institutes has a specific technology area which they focus on, and ours is to accelerate the development and application of innovative lightweight metal production and manufacturing technologies to benefit both U.S. and commercial defense markets. So we have three pillars that we essentially focus on. The first is technology development, finding new ways to enable lightweight solutions, whether it be through design, through manufacturing process, or even a materials swap for a particular component. But our researchers across the country are working on a number of projects in that direction, and you can see information on those projects at lift.technology as well. We also focus on transitioning that technology into the marketplace. Too often, these research is done and these solutions are found, but they sit on a shelf because of what's called the Valley of Death, as I'm sure you guys are familiar with, and there's no real connectivity between the research that's done and transitioning it to the market. So our goal here and at this institute and the other institutes around is to do just that and help find a pathway to put those solutions into the marketplace. The other focus we have is education workforce development. That is in order to enable the workforce of the future. As you guys, I'm sure, have heard, there over the next decade, there'll be 3.5 million manufacturing jobs open in this country, and 2 million of them are expected to go unfilled because there are not enough people working towards either those credentials, those degrees, whatever it happens to be. So our goal is to do just that and help sustain and make sure the pipeline of workers is robust moving forward. Again, you can read more about Lift at www.lift.technology. I did want to update folks on one other item. We recently, just as early as last week, held a ribbon cutting on our facility. We are co-located with IACME, the Composites Institute. They are headquartered down in Tennessee, but they have their vehicle scale-up facility here in Detroit. And we held a ribbon cutting just 2 weeks ago in Detroit, and we are happy to unveil the high bay with our manufacturing equipment that includes what you see on the screen now. This equipment is available for people to come in and do their R&D work, do some prototyping work. Just give us a call, contact us at communications@lift.technology, and we will get you squared away as that equipment is all coming online. Some of the services we're providing are listed on your screen as well, from engineering services to program management to product design and contract manufacturing, and even reverse engineering. So we are happy to have unveiled this. We did it on Manufacturing Day. We had some of our community and state stakeholders in the building as well to help us celebrate. So if you were not here for that, please come on by and take a look at us down in Corktown, in the Corktown neighborhood of Detroit. With that, these liftoff webinars are a partnership between LIFT and the center, Michigan Manufacturing Technology Center, which is based over in Plymouth, Michigan. They are working with us to help put these on to enable some of our smaller companies that are working on real innovative solutions in the lightweighting world, to give them an opportunity to talk about what they're doing and some of the real excellent ideas that are coming out of these smaller facilities. So I wanted to turn it over to the center to talk about a little bit more about what they have going on. I think we have Edith on board to talk about that.
Hello, everyone. This is Edith Wiarda at the Michigan Manufacturing Technology Center in Plymouth, Michigan. We are the Michigan location of a national network called the Manufacturing Extension Partnership, funded by the National Institute of Standards and Technology. We provide assistance to small and mid-sized manufacturers, consulting assistance with regard to operational efficiencies, and also with regard to growth opportunities, evaluating those opportunities and implementing them. We are very pleased to have this partnership with the Lightweight Metals Institute, LIFT. We encourage small and mid-sized companies to seek out membership at LIFT, particularly if you have technologies that you're developing that you think would have value to the manufacturing marketplace. And we're delighted to be helping to bring these seminars to fruition. Thank you, Joe.
Thank you, Edie. And yeah, the center really is a great partner for LIFT and for the small manufacturers in and around Michigan. So we value their partnership, and they've been fantastic in helping us bring these webinars. So please check them out as well if you are a small, medium-sized manufacturer, and see how they can help you grow and operate in any of the services that you see listed on your screen there. So with that, I'm going to turn it over to our featured presenter for the day, Ravi Kunju, Vice President of Manufacturing Solutions for Altair. He comes to us from with over 20 years of experience in applied advanced numerical methods and analytics which solve complex problems in the areas of computer-aided engineering and manufacturing process and business intelligence. After stops at Ford and Chrysler, Ravi is now at Altair. We had some stops in product design, software product management, as well as some executive roles in global sales, regional management, and strategic marketing. But now he is currently responsible for product strategy, global business development for the entire framework of computer-aided design, or computer-aided engineering, covering traditional and additive manufacturing. So with that, I'm going to turn it over to Ravi, and thank you very much for presenting to us today.
All right, and thank you all for joining the webinar today live, and also for those of you who are watching this at your own pace, at your own time. The title of my presentation today is Lightweight Metals Enabling Software, and I'm going to develop a framework about what we are trying to do in promoting and enabling lightweight metals design and manufacture. So my presentation for today will basically we'll start off with looking at the manufacturing trends and establish why there is so much focus on lightweighting today. And we will, as a process, I will introduce all the attendees to the concept of topology optimization and examples of. After that, we'll get into real examples of emerging topology optimization and some of the newer methods like 3D printing and additive manufacturing, and as well as traditional manufacturing processes. And we'll look at a few examples in casting that I've kind of handpicked from the examples today, because this is the folks here are mostly focused on the manufacturing aspect as well. And we'll develop a framework for efficient concept design and manufacturing, and we'll conclude based on the examples that you've seen today. So that's the flow of my presentation today. And so let's look at the manufacturing trends around the world. This was a report that came out of Deutsche Industry Bank a couple of years ago, and it was a very comprehensive report. And I usually start off my lightweighting presentations with this because it's pretty compelling. If you look at the comprehensive report, the three things that were distilled from the summary of this report, it was a pretty big report, as I said. The number one thing that they said in the manufacturing around the world was that lightweighting is the number one topic of contention among all the manufacturers today, for obvious reasons, for energy conservation, for environment pollution, and a lot of other considerations as well, and also in general efficiencies of the structures that they are working on. So, having established that, the interesting fact that this report also mentioned was from 1975 to 2035. If you look at the trends of utilizations of different types of material, and they predict, looking from 1975 to 2035, they say the conventional steel, which was in use, 70% of what was being manufactured in the 70s were made out of conventional steel. And they predict by 2035, that's going to reduce to less than 20%. And this is what we're talking about, is conventional steel, less than 25 KSI. Great. And they're saying that high strength steel and alternative material is going to increase in utilization, and they're going to climb up. And aluminum and magnesium, already you see it in some of the newer vehicles like the F-150 and so on and so forth, a large utilization of aluminum and also magnesium right now in the Chrysler Pacifica and in the tailgate, which is completely casted actually. It's pretty compelling for those of us who've been in manufacturing, the innovative ideas that are coming in. So having said that, the 3 points, again, to summarize, lightweighting is absolutely becoming critical. That's what the report claims, looking at all the manufacturing issues around the world. Steel usage is going to drop below 20%, and aluminum, magnesium, and other alternative materials are rising. And what that means is that we have to innovate. And over the years, what has happened is the design community and the manufacturing community have pretty much drifted apart, where the design community throws something to the supply chain and then says, hey, go guys, figure it out and make this, okay? And as a result, what has happened is the complexity in manufacturing processes has gone over the roof. And because the product design and the manufacturing communities have worked in their own individual silos. And there is a great need and higher levels of early collaboration with common tools across these silos, the product design and the manufacturing folks. And that's what we are trying to address. We're trying to bring them together, because if we look at manufacturing simulation software in the past, they have thrived typically on the complexity that has arisen because of the two different silos. And often they're too late to make any changes in the product design, and also too expensive, A, to learn because of the process complexity, and B, they're too expensive to modify designs at that later stage, and they're expensive to learn to use as well. So as a result, what we are trying to do under this new paradigm of lightweighting and new materials coming in, we feel that you have to start manufacturing feasibility right from the design stage. And that's the kind of approach we're trying to take with a whole slew of products, which I'll talk in a second, where we're focusing on simplicity, coming in from the left, where we're coming in right from the product design side with early design and process validation, and also offering tools that are affordable and not something that bankrupt the companies and trying to use them. And at the same time, we also want the solutions to be fast, absolutely easy to use, so it's part of the workflow, and also accurate. We don't want to compromise on any physics involved in there. So this is the kind of framework that we're building for accelerated lightweighting, and we've done that very successfully with a product called Inspire, which was basically targeted towards all the designers. In the old days, and I'll talk about topology optimization as I promised earlier, but the topology optimization software for generating bionic structures to meet the requirements of loads and boundary conditions were typically in the hands of advanced CAE users. And we changed that paradigm by bringing it into an Inspire framework, which is basically designed for designers so that the designers can start generating those shapes to meet the purpose, and also evaluate as a process whether the structures that they are producing are manufacturable or not. Into that context, we've added casting feasibility solutions within Inspire. We've added stamping feasibility within Inspire. And we also have standalone products to address the casting market, address the casting components, and also for metal and polymer extrusion. And we also have solutions for sheet metal forming with click to form. So these products are called click to cast, click to extrude, and click to form. But all these products in conjunction with Inspire, which generates the shapes, is what we call as the framework for accelerated lightweighting, where we're pushing the boundaries of design and manufacturing. And specifically, I want to mention simulation-driven design and manufacturing. And obviously, we will look a little deeper on casting, because I think that's easier to understand, and it's one of the oldest ways to manufacture things, and we'll concentrate on those two areas today, and also talk about bionic structures. So now, before we get into what Inspire is and what topology optimization is, and these are the products, I do want to mention that what are bionic structures? In the 19th century orthopedic surgeon, Dr. Julius Wolff, had mentioned, I just want to read this verbatim, and I want to concentrate on a few things. What he said was he took inspiration from, as a consequence of primary shape variations and continuous loading, or even due to loading alone, bone structure, basically bones, changes its inner architecture according to mathematical rules, and as a secondary effect, and governed by the same mathematical rules, also changes its shape. So what he basically said was that the bone structure internally grows based on the loading conditions. Not only internally, but also externally, the shape changes based on the loading conditions. And so this was basically the inspiration behind topology optimization that we introduced about 20 years ago. And surprisingly, the biggest interest that came in, the first adopters of those were actually the aerospace folks. And let me establish what this is. So for those of you who are engineers, I presume most of you are in this call, how does this work? In most of the simulations, if you look at simulation, you basically take a component, apply loads and boundary condition, and say whether it meets the required loading conditions, does it meet the requirements. But in topology optimization, just does the reverse, where you define a design space, you apply the loading conditions, you apply the boundary conditions where you're holding the component, and so on and so forth. And then once you apply it, it automatically generates the shape of the shape. It generates a shape that basically meets the purpose. So you're coming backwards, where you're applying the loads and boundary condition. Like for example, here you have a square space, and you're applying uniform loading conditions, and you're holding it at two ends, and on the right hand side it automatically comes up with a shape which looks like your bridge structure. For those of you who can recognize this is one of the older structures. You could see one of the first bridges in the world designed by the Romans who took this structure. They figured this out, but now with mathematical computation tools available, you can generate, and we're going to see a lot more examples of this as well. So the red areas that you see on the right-hand side, what Inspire or OptiStruct in the background is doing is automatically giving you the load path, the optimal load path. And the red areas is where it's telling you you need to have put mass there. And the other areas, you can just take it off. There is no necessity for you to have any mass in those areas. So that's what we call as a density plot. And that becomes a driver. It gives a template for how your design should look like. So let's take another example. This was a Volkswagen bracket that we did many years ago as well. And I think it's a good example to show you. This is a bracket. We took the loads and boundary conditions on it, and if you look at it, what we do is we make a complete design space, and then we start iterating, and we start removing the material where it is not necessary. And on the right-hand side, by the end of about 16 iterations, it basically comes up with a complete structure that meets the requirements, the loads and the boundary conditions. So how does this look? If you look on the left-hand side, that is the original design under the same loading conditions. You can see the red areas are actually showing you the high areas of high stress and plotted to the same scale. And on the right-hand side is the optimized, topology optimized bionic structure that has 64% reduction in stress under the same loading conditions. The total displacement is 52% less. And guess what? It's 31% lighter. So this is an amazing principle of topology where optimization, where you are creating designs that meet the purpose and at the same time reducing the weight. So it's completely optimal from that perspective. So what we build, as we build this, one of the important things of topology optimization is if you combine free-form optimization that I showed you with some of the newer technologies, with additive manufacturing and traditional manufacturing, you get tremendous amount of geometric freedom. It injects tremendous amount of innovation, and it gives design individuality, meaning that you're not creating the same component that you created 10 years back, but you're basically creating a component that meets the purpose very well. It's individualized to that particular form. The form is perfectly fitting the requirements. And it also helps accelerate the product development because very, very quickly you're able to generate these shapes instead of trying many experiments. So based on the loading conditions, you're generating a shape that meets the purpose much more quicker than ever before. Having said that, I always talk about subtraction before addition. So I'm going to give you a tremendous amount of examples as food for thought, as lightweighting examples, where we have looked at 3D printing itself, metal printing as enabler, and also we're looking at how some of these new technologies can combine with traditional manufacturing to create tremendous amounts of opportunities and tremendous amounts of accelerated lightweighting products. So let's jump into that. Let me give you the first example here. And this is something that we just released the last month, this hot off the press. And this is complete front-end structure remodified for the Volkswagen Caddy. And exploiting the entire geometric and design freedom, it's a shell construction, it's completely hollow, and it's a combination of hollow and lattice structures. And it's completely new aesthetic design. And there's a lot of firsts in that. The package optimization, the package is completely optimized, the function and integration of multiple components into one assembly. And so instead of having hundreds of parts, you have a lot fewer parts by beautifully integrating all the requirements. And it also has a passive management, thermal management, as well as active thermal management, and also the enclosure. The hollow structure also acts as a reservoir for the windshield washer tank, as well as any of the fluids required for coolant and so on and so forth. So multiple purpose, and I want to show a quick video of this as well, the making of this, where this was completely 3D printed to create this front structure. So indulge with me here. There's video in this, there's music in it. I have muted the music, but basically the whole idea was to start from scratch the entire design. It was individualized, it's completely integrating multiple components. So lightweighting not only is generating lightweight structure, but it also gives you opportunity to combine multiple components into one single component as well. So in this case, you're seeing that it was also optimized for the front end crash, in addition to having the shape optimized for aerodynamics, and also passive and active thermal management as well. So this was 3D printed with our partner EOS and CSI, and we basically created this very compelling. And those of you, if any one of you is going to be at the Formnext show in Germany next month, you will have an opportunity to see this firsthand as well. The whole vehicle will be there with the front end structure. And you can see that the components that were basically 3D printed, the individual pieces were then welded together. And you can see the brake cooling there, and you can see Altair's name in there as the driver for the design concept here. And you can also see a combination lattice structure as well as traditional structure, and that is the front end of the Volkswagen. So EOS, Reyes, AP Works, and CSI were the partners in this particular case. Now, if you want more information, you can get that from there. This is one example, a compelling example, to show you what is possible with the bionic structures. I also want to show you another very quick concept here, the complete frame, where you define the design and the non-design space. You apply the loads and boundary conditions. This is a motorcycle frame that we worked on. You define the optimization parameters, and then you come up with a bionic structure that you see on the screen. And then you basically reanalyze it and saying, hey, the bionic structure that's coming out, does it still meet the requirements? So you can do a re-engineering, reanalysis of that, and then look at it. And this is the final product that you see. To summarize, this is the entire frame is only 35 kilograms in weight. This is an electric motorcycle. The entire the vehicle itself is 35 kilograms. The frame, the lightweight frame, is 6 kilograms in weight. And also do bear in mind that a special metal Cal Malloy was created for printing this particular thing in partnership with EOS and AP Works. Very compelling story of what is possible with these bionic structures. I want to give you another example, similar example. This went from the road. We're moving from cars to motorcycles, now into space. This was a bracket for a telescope up in this, and one of the probes that went out into space. The original design obviously was taken out, and the loads and boundary conditions were applied to this. And once the design was swapped, the design space was said, okay, this is the design space we're going to work on. And both the stiffness was increased, at the same time the mass was decreased to come up with this bionic shape that you see, super stiff and at the same time super light. And you can see how the shape actually grew. And if we swap in, this is the final part that was actually printed and sent over to the space. Again, this was in partnership with the EOS. If you summarize this, there's 43% weight reduction, and the eigenfrequency, that is that kind of measures the stiffness, went from 70 hertz to 90 hertz, and improved static behavior, strength, and stiffness. So in addition to being light, it also is phenomenally engineered for the purpose. And there are a lot of other examples that you can see as well that we have done across the board. But I do want to zero in on a few other things. Like, let's look at from a manufacturing perspective. Let's say, for example, I have a robotic gripper here for a robotic arm. And this is what you're seeing in the background is Inspire. The way I'm trying to help you understand the process. So in this, you're applying the loads and boundary conditions with a very simple set of menus that you see on the top. You apply the loads and boundary conditions. And so you took the original design, you created a whole rectangular kind of a space around it that envelopes the whole area, and then said, remove the old design. I'm going to work with this space, apply the loads and boundary conditions, and it Inspire automatically generates the shape that meets the requirements and tells you that this is what the shape should look like. And based on that, you say, okay, this is what I'm going to make. And now the question is, how are you going to actually make this? In this particular case, we said, let's not 3D print this part. Let's see if we can cast this component. And obviously, we have tools in there to take the geometry that comes out of Inspire and clean it up and create some really nice, smooth surfaces to a function called polynerbs that we have that create solids, as you see, as and when you create those surfaces that the Inspire basically gives you those surfaces from the topology optimization, and you can just go envelope it with a very smooth surface using polynerbs and create some really nice geometries. Now the question is, can we actually cast this? So what we did was we took the original design and we ran a quick casting analysis using Quick to Cast. And then you see on the left-hand side the original design. On the right-hand side, we're pouring the casting in there and then trying to see if what are the likely issues that are likely to happen in this case. So very quickly, you see that it's drawn to a different scale actually, but I'm showing you the porosity, which is a measure of when materials shrink. When you're in casting, one of the biggest thing that the casting guys will always talk to you about is porosity, where when material changes from a liquid to a solid phase, there is a shrinkage in volume, and usually that shrinkage accumulates in the areas which are the last areas to solidify. So, and if you look at in this particular case, it's showing you a big blob of porosity right in the center where the junction is. Whereas on the right-hand side, if I measure the area of porosity, there's 88% reduction, went from 34 millimeter cube to 4.3 millimeter cube in one location. So what it's trying to tell you is that not only have you lightweighted the structure, but interestingly, it also becomes easier to cast because the porosity is 88% less. So we saw where the actual big porosity was likely to be, and then we put a riser in there and evaluated whether this riser could feed the porosity in there. And then we did a quick analysis on this to show you the contour that you're seeing there is the last areas to solidify. The red area is the last area to solidify. So you can see that basically the riser is the last area to solidify, telling you that it has fed the porosity in that region. So this is, again, 30% reduction in weight on this robotic gripper. Let's look at some more examples to give you the whole idea of what freeform optimization in combination with additive can do. This was a student racing car that we worked on. It was an electric racing car that we worked with a European team. And we were designing the wheel upright that's shown in red color on the right-hand side. And it's a very critical component in this racing because that's the main component that takes the loads from the driving loads, whether you're braking loads, the cornering loads. This is the main component that transfers the load from the tires over to the suspension. So a lot of complex loading going on there, and we wanted to look at what can we actually do to reduce the weight and improve the performance. So in this case, that's the original design that you see. The original design was machined to look like that, and a lot of different boundary conditions. I don't want to get into details of this, but if you look at it, we looked at the loads for different maneuvers. We looked at loads for the braking, for cornering, and so on and so forth. And we put all those loads in, and at the end, you get this bionic topology optimized structure that you see on the right-hand side. The question, and also we compared the bionic with the original design, and you can see that it's drawn to the same contours levels, and you can see that the stress in the component is much lesser than, a lot lesser than the original design. And we also ran a fatigue analysis on this as well, and I'm not showing that here, but we also did that. And in addition, we also looked at the casting, which I'll come to you in a second. So basically, this is the original design, and this is the bionic structure. And this is not a typical component at all. If you look at it, this is not a design that any casting, anybody in the casting would have traditionally seen, because A, it has a lot of undercuts as well. And at the same time, it's impossible to cast with traditional methods. So how did we do this? Can we even cast this? So we asked this question, and then the first thing we wanted to explore is, how can we very quickly identify what are the areas where you want to start pouring the material? And we use something called an investment casting process, and I'll come to that in a second. But what is the area from where you want to pour the material for casting? So we studied the gate influence. We did the gate influence study over for 40 different combinations, but I'm showing you only 3 different cases here. And on the first, you have a gate on the left-hand side on the top, and then 2 gates, the second one and the third one, a gate at the bottom. So we very quickly analyzed these 3 shapes, and you can see that if you look at the left-hand side, we deemed that this was not the best because there's a lot of turbulence and there's a lot of different fronts coming and meeting at the different times with different temperatures, so introducing a lot of other issues that could happen in the casting. Here as well, it was the same thing. You had a lot of turbulence when you had two gates. So finally, we went ahead and had a single gate at the bottom to feed this casting off, which was much less. And we also evaluated, and this is how we use click to cast. We took the shape in. It's a very easy to use environment. You just have to go in and bring in, and you can do detailed analysis as well here, but here we're showing you a quick assessment of identifying where you're going to put the gate location. And within 5 steps, you can define what kind of material it is, what kind of mold it is. Within 5 steps, you can do the entire casting simulation, and within your desktop or a laptop. And here you've defined the gates. You're defining the process parameters. You're saying, well, you're basically doing the filling and the solidification. It's an investment casting process where I'll show you in the next screen, and then you evaluate where the casting, how the flow is. You do both the flow as well as the solidification analysis on this, and you can see what are the last areas to solidify, how the vectors are while the flow is happening, and you can look at the solid fraction, which is basically the last areas to solidify. And we did identify a couple of areas where there could have been porosity, but the porosity is very, very small. So we basically went ahead and actually, if you summarize it, we and took the original design, and what we did was we 3D printed the pattern. And the investment casting process, if you do not understand the process, I'll just take a second to explain that. It's one of the oldest in casting processes, where you, in the old days, they used to carve and wax, and the wax was basically put into a slurry of sand. The sand sticks to the wax, and they take the whole thing into an oven. And when they put it in the oven, the wax melts off, leaving the cavity, the sand cavity, and then they would pour the material into it. And that's exactly what we did here. We printed but in this case, we 3D printed using a voxel jet printer, and we printed it in PMMA material. And basically, this kind of wax like a compound, which basically melts, and you put it in the oven, and then you basically pour the cast. And on the right-hand side is the final casting that you see. Completely, in this case, the weight reduction was almost the same, but the performance was way, way, way better. Okay, so that's another way of looking at what we were able to achieve in this particular case. Let's give you another example. This is something that we worked with Amazoni in Germany. It's a field equipment. The yellow area is the area that of concern, where we modified that rocker arm for the it's a farm equipment called a disc, which is used for farming. And this rocker arm needed to be redesigned. So we basically took the same approach, created a bionic shape. By now you know what it is. We also evaluated whether this structure, the bionic structure, can be cast. And we did multiple analysis on this, looking at the flow, looking at the solidification by putting multiple risers onto the structure, whether the risers are feeding into possible areas of porosity. And once we came to a conclusion that is possibly castable, we went ahead, and actually the interesting thing was we 3D printed the entire mold. In this case, we 3D printed the mold in a voxel jet printer, which is basically 3D printing the sand. And let me show you the process for those of you who may or may not have seen. Again, if you look at what I'm trying to establish is we are trying to turn conventional engineering on its head by combining optimization and also the 3D printing methods and so on and so forth. And here, this was the actual the 3D printed mold that was built, and you can see how big this is. And it's actually in 3 parts, and I'll show you that in the next slide. And it's printed in sand. And then if you look at this here, the 3 of these parts were fused together to create the entire die, and the cast was actually poured. So this is a perfect combination of, again, using conventional, traditional manufacturing in conjunction with the new technologies available for 3D printing. This was the final part that was cast, so you could see how bionic the structure is. And we actually did 2 different combinations of this. One was for traditional casting, if we wanted to do it without, taking into account whether you can cast it traditionally. But we went ahead with a more radical shape on the bottom, which combines multiple components into one component, and it's impossible to cast this traditionally. So we 3D printed it, and if you look at it, the entire optimal casted part was 35% cost reduction. It's an integral part, and also the cost of if you're looking at integrating components into it, the cost factor, the cost savings are even higher. For example, the original design had 16 meters of weld, and as soon as you start welding components, you will also see that there could be other issues with respect to residual stresses, with respect to dimensional accuracy, and so on and so forth, and as well as assembly issues. But all those things are reduced by having one structure that combines multiple components into one. And in addition, the weight was 11% less, and also 75% lead time reduction, because you're reducing the entire tooling time by printing the entire tooling in one shot. So there's tremendous amount of savings in this particular approach. I want to also take another example, and here in this case, I'm moving from a sand printed mold to a 3D printed die for an injection molding die. Okay, so in this case, what did we do? It was a very interesting case as well. We worked with Protek on this in Germany, and 2 things. This structure that you see on the right hand side was optimized both for structure as well as thermal optimization. So it was structurally optimized and thermally optimized, and we'll see that in a second. So again, the same concept. You define a design space and you define a non-design space, and you optimize it the same way. You come up with a bionic structure. And in this case, in addition to that, we also looked at the thermal side of it as well, where we ran AccuSolve, which is the CFD solver within the Altair portfolio, to make sure that we're removing the heat dissipation is also extremely efficient. So not only did we optimize it thermally, but we also optimized the heat dissipation, and the whole die in this case was 3D printed. And you can see the original design on the left and the same the plastic design on the original die versus on the final die, that you could see that the heat dissipation a lot more quicker. Again, 25% faster in production, 75% reduction in the die itself, and 25% lower tooling lead time, because there is not tweaking anything. It's ready to go right off the bat. So I walked you through multiple examples, and by this time you probably understand the benefits of what topology optimization can do even in traditional manufacturing. So what we are trying to do is to build a framework. You're seeing a mechanism here. So in this Inspire environment, you are taking a mechanism like this and very quickly optimizing it. So you're taking the loads from this mechanism based on how the things are moving, and you're taking the loads in there, and you're generating this bionic shape. In this case, you'll come up with a baseline structure. Once you've come up with this baseline structure, you can go to a quick button. I'm going to pause this for a second. You can click this under manufacture. You can click this button and then say, quickly evaluate the casting for me. And then it'll ask you a couple of questions. And then on this bionic structure, you can go ahead and evaluate the casting feasibility within this environment. So right off the bat, as I established earlier, we're giving these tools to the hands of the designers, where as and when they're generating the shapes fit for the purpose, you're also evaluating the manufacturability. Right now, we're seeing the solidification time. The red area is showing you that that's the last area to solidify. And I'm also looking at the solid fraction. That is basically where exactly am I likely to see porosity. And I'm cutting the section. And as you move, you can say, hey, that's the red areas are the areas where I'm likely to get porosity. So this is something that a designer can equip himself with while he's developing the process, or he can communicate with the manufacturing community saying that, hey, this is optimized shape. I see three zones where I'm likely to get porosity. So please go ahead and do whatever is necessary. Or I can tell you, I can refine this model and I can put the risers in there, and I can tell you that these are the most optimal risers for you. So that way you can evaluate very quickly and then reduce the entire manufacturing process as well. So we've gone from defining one mechanism to optimizing the structure and evaluating the manufacturing feasibility and giving meaningful information, whether it's a manufacturer who is doing this or whether a designer who's doing the whole thing, vertically integrated company that's doing the entire thing. You can have one framework to do the entire design as well as manufacturing. So that in a nutshell is the lightweighting framework for accelerated lightweighting that I just presented. This is a combination of Inspire for topology optimization and our verticals in quick to cast, quick to extrude, and quick to form. Of course, today we saw only the casting components of this, and we will be more than happy to present at a later time other technologies as well, including sheet metal forming and metal and polymer extrusion as well. So with that, I just want to conclude a few things. Topology optimization has been a driver in design and manufacturing. It's getting more widespread, especially with additive manufacturing initiatives. The right topology optimization tools are extremely effective for lightweighting initiatives, and also I would say the bionic designs arising from Inspire topology optimization, in addition to being lightweight, they're probably friendlier for manufacturing as well, as we saw in some of the examples in the castings. And I also want to mention that the manufacturing feasibility simulations are extremely cost effective when done in conjunction with product design, not after, meaning that you have to start evaluating manufacturing feasibility as part of the product design process as well. And that's what we feel would really help in accelerating lightweighting across and give ideas for OEMs and other manufacturers to basically look at a holistic approach and look at the whole design with the eyes of manufacturing as well. And at the same time, take the latest and the greatest framework to create bionic designs to meet the purpose, and also simultaneously evaluate different manufacturing methods to make those radical shapes. So that's what I had, and I want to hand it over back to Joe.
Thank you very much, Ravi. Appreciate the presentation. And it goes back to what I've said in the beginning of the call, is that when we talk about lightweighting, we talk about everything from material to manufacturing process to design. And I think you walked us through that very nicely, especially when it comes to going back to the design piece. So again, if anyone does have questions, please use the GoToMeeting taskbar and send your question to the organizer. We did have one that came in. Ravi, asking about the very first example you showed about the frame that was done on that car. What air conditioning component, can you speak on that? What air conditioning component is integrated into the front structure? Is it liquid line? Is it suction line? Is it a receiver, dehydrator, or some other kind of system?
I think the combination, there is passive as well as active cooling in there, and the idea was to use it for the active side. It was connected to and it was acting as a reservoir for the refrigerant. And I can get more details about this as well, and it should be on our website as well. I'll be more than happy, whoever it was, to give more additional information about it as well.
Great. And for anyone else, they have again, if you don't have any other questions, but would like to contact Ravi about this presentation or about other work that they have going on at Altair, you see his contact information on the screen. So please send him a note. So I don't see any other questions coming in. So we certainly appreciate everyone joining today. Please check back on the lift.technology website for future liftoff webinar presentations. We'll have one in November. We'll take the month of December off. due to the holiday season, and we'll come back in January after that. So again, thank you, Robbie, for your presentation. Certainly appreciate that, and thank you everyone for joining. We look forward to seeing you in November. Thank you.